so jealous.
All right. On page 30, we were looking at transformations yesterday, how we can take a beginning graph and start to move it, shift it, flip it, stretch it, do a whole bunch of different changes to it. And I believe we left off at the bottom. Did we finish both of those? We're good? Okay. We talked about the order, RST. Okay. We do have one more thing to do with these two graphs. We're going to identify the domain and the range of both of those graphs. I know you've heard of those words before. The million-dollar question is, do we remember or do we know what they mean? Some say yes, some say no. What's our current understanding of domain or range? X and Y. Basic definition. Okay? Domain represents X values. Range represents Y values. So what we're doing is trying to identify or show the X values that would work if you were to plug them into the equation. Graphically, we're trying to figure out on a picture, where does an X value have a Y value? Meaning, where is there a point? Okay? So I'm going to show you kind of my shortcut way to determine these, because again, we might be familiar, we might not be. Maybe we're good with finding domain and range, maybe we're not. But this is how I go about it. Very similar to the vertical line test. Remember doing that way back when? Okay? I want you to put your pencil down on your paper, and we read a graph from left to right, just like we do a book. So if you put your pencil down on the left-hand side, I want you to look at your graph and ask yourself, how far left would that graph go? What do you think, Eli? How'd you know? Yeah, we got that arrow, right? That arrow is signifying that the graph will continue in that path. So the furthest left this graph goes is negative infinity, meaning the smallest X value we could plug in is negative infinity, whatever that number might be. All right, so again, we have our pencil on the left-hand side. I want you to start dragging your pencil across the graph and ask yourself, where does the graph stop? Which X value? We're talking about domain. 1. Okay. Notice how we're creating an interval. Okay, we're kind of identifying the lowest point and the highest point, or the beginning point and the ending point in terms of the X's. Are we okay with where those come from? Yeah? Okay, there's a little bit more to it though, because we're going to get used to notation and reading and understanding math language this year. We're going to use, let me ask you this question. Will you ever reach negative infinity? No. So I want you to put a parenthesis. A parenthesis is a symbol that we use in interval notation. That means you will never reach or never equal that value. Does the graph reach or equal an X value of 1? Yes, we have a closed dot right there. So we're going to use a bracket. A bracket means you do equal or you do touch that point. Okay, so domain are X's. We're going to drag our pencil left to right and simply ask ourselves, where does the graph start? Where does the graph stop? Okay, now range, we're going to do the same thing, but for the Y values. So put your pencil at the bottom of the graph, and this time we're going to start to drag it up. Where does the graph start for the Y values? -3. Good, okay. Continue to drag your pencil. Where would the graph stop? Infinitely, right? We have that arrow. It's going to continue to go to the left, like we said before, but it's also going to continue to go up. So it actually never ends as you drag your pencil upward. Can we touch the Y value of -3? Yes, there's a closed dot. Will we ever reach positive infinity? No. So we use a parenthesis. All right? I want you guys to try the next one. Drag your pencil. Find domain and range for H. Now I know some of you might have more than one graph on your grid. We're only doing the final one. Okay, so if you did not erase the previous graphs, make sure you can find the final one. All right, this should be real quick. Dragging your pencil left to right, where does it start? 1, where does it end? Infinity, good. All right, so 1 to infinity. Can we touch 1? Yes, bracket, can we touch infinity? No, parenthesis, good. Let's do the same thing for range. We're going to go low to high. How low does it go? Negative infinity, good. The arrow is going to continue downward. And drag your pencil up, where does it stop? 3, good. Can we touch negative infinity? No. Can we touch 3? Yes, bracket, yes.
Does it matter which order you have those in?
Like if you had 3 comma negative infinity?
Yeah.
Yes, it does. Good question. Okay? Order does matter. When you're talking about an interval, the first item usually represents the smaller value. Okay? So small to large, just like a number line. How do we do with domain and range? Good? Okay? We're going to do more of that as the unit continues, but this was like a good intro to that. Okay? The rest of today, though, we're going to talk about the transformations that we were exploring yesterday. So on the next page, we have this really nice, organized go-to chart that we're going to fill out. We talked a lot about different movements yesterday. We just got to make sure we can identify them appropriately. Okay? Make sure that we know when it goes up, right, left, down, flip, stretch, all those different options. We're going to step it up a little bit today because we're going to talk about how these shifts or changes affect the coordinates, meaning the x and y variables or those points. Okay, we didn't really do any of that yesterday. But let's see if we can dig deep. If you need to reference yesterday's square root graphs, you can. Okay? If we add on the outside of a function, how does that change the graph? Go to Eli. It goes up. Okay, so if we're adding a number c, it'll go up c units, whatever that value might be. Okay, we did that yesterday. But let's think about this. If we're shifting a graph up, how does that affect the points? Can you think about which variable you are changing if you move a point up?
Translation.
It is a translation, okay, because we're moving it up. Do you affect the x variable or the y variable if you move a point up? Okay, so not only do you affect the y value, but you increase it. Okay, so let's think about this. The x value stays the same, but if we're increasing the y, that means we're adding something to it. We're making it larger. Okay, we're specifically adding that c amount, however many units we move it up by. All right, what if we subtract something on the end? Bless you, bless you. Going for 3? No? Okay. What if we subtract something on the end? Down, good. Down that many units. If you're moving a graph down, which variable are you affecting? The x or the y? Yes?
The y.
The y. And if you're moving it down, you are decreasing, meaning minus. Good. All right, so this would be y minus c. Really good so far. What if we add a number inside of the function? Yeah? Left. Good. It does the opposite of what you'd think. Okay, left c. So if you're moving a graph to the left, which variable are you affecting in terms of its points? The x. How are you affecting the x if you're moving it to the left? You're decreasing, so we would have to subtract the c value. Notice how this is where it gets a little tricky, okay? In the equation, we are adding the c, but in terms of the points, we are subtracting the c. Can get confusing. Let's make sure we keep that straight. All right? Kind of process of elimination or educated guesses here. If we subtract on the inside, that's going to move it right. And if we move a graph to the right, we are increasing the x value. So we would add that many units to the x number. Good so far. What if we have a negative on the outside of a function? This is where we get different kind of changes. Yeah?
Left over x-axis.
X-axis, good. X-axis reflection or flip, whatever word you want to use. All right, so this one might be a thinker. If you're taking a point and you're going to flip it or fold it over the x-axis, which variable are you affecting? And how is it changing? Yeah, Emma? The y variable, good. So the y is changing. How is it changing? Yeah, Keith?
Negative or positive or positive.
It's flipping sign. Good. Okay, maybe we might need a visual for this. Okay, think about, let's see, we'll draw a little graph here and we'll plot a point. That point has a specific x value and y value. We might not know what it is, okay, but we know it has an ordered pair. If you take this point and fold it over the x-axis, notice how the x value stays the same, it's still in the same spot, but the y value changes from positive to negative. Okay, so the y value is switching sign. Even though we flip it over the x, the y is what changes. Again, can get tricky. We got to make sure we keep them straight. All right, yesterday we started to combine some of these transformations. Maybe we can do more than one of them. So what if we were to add c on the inside, but then add another number on the outside? How would that change the graph? What do you think, Eli?
Left C and up. Left C and up D.
And up D, all right? So if we're moving something to the left, we're affecting the x, but if we're also moving it up, we're affecting the y. So it looks like we have two changes. Left would mean we got to subtract from x. Up means we got to add to y. Do you guys think you can do the next three?
No.
Oh, I think you can. I have faith. Give it a shot. How do we do? Check your answers on the board. Three for three? Batting 100? Can you get the baseball reference? All right. Let's try the next one. What if we have a negative on the inside? Yeah?
I think it's y-axis.
That's a y-axis flip. All right. So which variable are we affecting in terms of the points? The x. And how does the x change? Negative. Good. Okay. Let's see. We might need another visual. Let's say we pick a point in the first quadrant. It has a specific x and a specific y. If we fold that point over the y-axis, it'll land in the second quadrant. Notice how the height, meaning the y value, stays the same, but the x changed from a positive to a negative. Okay, so even though we're flipping it across the y-axis, the x variable is what's affected. Can get tricky, but we got to keep them straight. So far, so good. Now, the next one we didn't really discuss yesterday, but maybe we can think about it. Okay, absolute value. How would that affect the graph? Or the points? Think about what absolute value means. What do you think, Eli?
X always positive.
Not the x, but something is always positive.
Y is always positive.
The y is always positive. F of x and y mean the same thing. Okay, so notice how if we substitute in something for y, that's what we take the absolute value of. That would make any negative value positive. So all the y values are positive. So in terms of our points, the x coordinate doesn't really matter, but the y coordinate always has to be positive. So that's what we'll take the absolute value of. That one's not going to show up a lot. We are going to talk about absolute value graphs today, but maybe not necessarily that transformation. Okay? But we did do the last one yesterday. What if we multiply by a number on the outside? Yeah, that's a vertical stretch. Okay, so think about the word vertical. If you're vertically stretching something like an accordion or a slinky, which variable are you changing? Yeah, the y, right? So the x doesn't change, but if we need to vertically stretch the y, we're going to multiply the y value by that a number. Okay, yesterday that was 2, like where we doubled all the heights. We multiplied all the heights by 2. All right, so far so good. Good or very organized go-to chart. Everything that we kind of discussed yesterday. But what we're going to do today is kind of extend this concept. Yesterday we only looked at square roots. Today we're going to look at other types of graphs. And what's nice about these transformations is that they work for any type of function or graph you have, not just the square roots like we did yesterday. So let's first kind of go over some other basic graphs that we can start to change or move or affect. What does the basic or parent function look like for a quadratic? X squared. Yeah? No? What do you think, Eli?
It's kind of like the same with the square one when it goes up the y-axis.
Okay, so let's see, if we plot some points, we can plug in 0, 0 squared is 0. If we plug in 1, 1 squared is 1. Plug in 2, 2 squared is 4. If we try to plug in some negative values, negative 1 squared is 1, negative 2 squared is 4. We get that U-shaped graph, which is called parabola. Right, okay, so quadratic graph is a parabola, that U shape. All right, so every quadratic graph looks like a U. It just depends where it's located. Bless you. Did we shift it? Did we flip it? Did we stretch it? But they all look like a U. What about absolute value? Do we know what that graph looks like? Value. V. Yep. Let's pick some points. Absolute value of 0? 0. Absolute value of 1? 1. Absolute value of 2? 3? We can go on forever, right? Let's do negatives. Absolute value of negative 1? 1. Negative 2? Negative 3? There we go. V-shaped graph. Value, V. So what's nice about these parent functions, these basic kind of starting ones, almost every parent function graph will go through the origin. Remember how the square root started there yesterday? These also go through the origin. You have the vertex, okay, the bottom point, starting at the origin for both of these. So if it goes through the origin, it's kind of a basic starting function graph. These next two we may or may not be familiar with. Okay, so on the back we got 2 more. We're going to talk about a cube root. Let's plug in some points and see what happens. What's the cubed root of 0? 0. Cubed root of 1? 1. 1. Because 1 times 1 times 1 is 1. What's another value we can easily take the cubed root of? Good, Emma? 8. What would that answer be? 2. 2 times 2 times 2 is 8. So if we plug in 8, which is a little bit off our graph, we'll get out 2. Any other ones? Can we plug in negatives? You actually can, okay? You cannot take square roots of negative numbers, but notice how this is a cubed root, okay? It's something different. So what if I wanted to figure out the cubed root of negative 1? What number times itself 3 times would give you negative 1? Negative 1. Negative 1 times negative 1 times negative 1. So if you plug in negative 1, you get out negative 1. You can take the cubed root of negative numbers. So very similar, negative 8. Because that would be negative 2. Negative 2 times negative 2 times negative 2. So if we plug in negative 8, we get out negative 2. Kind of a weird looking graph, but if we play connect the dots, we're going to get this kind of curvy S looking shape going across the x-axis. All right, our last one is the cubic function. That's a power of 3. Okay, quadratic was power of 2 that we did before. So let's plot some points. Plug in 0, get 0. Plug in 1, get 1. Plug in 2, we get 8. That's a little bit off our graph. We can plug in negatives. Plug in negative 1, get out negative 1. Plug in negative 2, get out negative 8. And we'll play connect the dots. So it's a very similar graph actually to the cubed root function, but notice how this one goes across the y-axis, whereas the cube root goes across the x. Okay, very similar shape. So these are basic beginning parent function graphs. We're going to start to transform some of these right now, actually. So just like we did the square roots yesterday, we're going to do these new ones today. All right, so let's take a look at the bottom. G of x. I want you to look at the equation, and there should be something going on in the equation to kind of give you a little hint or a light bulb as to which parent function we should be using. What's in there that tells us the beginning graph we should start with? What do you think, Eli? How'd you know it's quadratic? Okay, so the power of 2 is signifying a quadratic function. So we need to begin with that parabola shape. Okay, let's go ahead and graph that. Okay. So since the power of 2 hinted us into the type of graph we need to start with, everything else in that equation is a transformation or a change. Okay, that power of 2 does not affect the graph. It tells you what kind you need to start with. So can we take a look at the rest of the equation and kind of pick apart how we're going to move this parabola? What are some changes? What do you think, Emma?
Times 2.
Would do, say it again?
The times 2 inside would go, make it move to the left.
Left 2, okay. Remember the inside does the opposite of what you would think. Yeah?
Down 3.
Down 3. All right, I think that's it. So again, the power of 2 is not a change. That's just telling you what you're starting with, okay, your parent function. So let's label our beginning parabola with a P, and we'll go through our order. R, S, T. We did not label any reflections, so we don't have to worry about that. We did not label any stretches, so we don't have to worry about that. But we do have some translations, okay, up, down, left, right. So every single point on this parabola, we're going to move left 2 units and then down 3. So go ahead and do that. This was our translation graph, so we'll label it T, and it's our final one, so we'll circle it. If you want to erase the parent graph, you can, which will just leave you with the final one anyway. Okay, but some of you like to see those changes. Okay, so square root, quadratic, absolute value, it doesn't matter. These transformations act the same way for any function that you have. What's going on in H to kind of hint us or give us a clue as to what we should start with? Yes? Absolute value. Okay, those are the bars. All right, so let's start with that parent function, that V shape. The bottom of the V is at the origin, and then we have those lines on both sides. Okay, slope of 1. So the bars are just hinting as to what shape we need. Those are not a change or a transformation. Everything else in the equation is something that we need to identify. So can we find any of those changes? Can we label them? Good. Emma, can you give me one?
The negative in the front will flip it over the x-axis.
All right, x-axis flip. Eli, do you want to give me another one?
Left one.
Left 1. Good, Emily?
Up 4.
Up 4. Good. Okay. Let's go through our order. RST. We did identify a flip or reflection, specifically over the x-axis. So instead of the V going up, we're going to flip it over the x-axis, which is going to make it go upside down. All right, so we'll label that graph R. We did not label any stretches, so one less thing we got to do, but we do have some translations. So the reflection graph, we're going to have to move left 1 unit and then up 4 units. Label it T and circle it for your final. But if you want to erase the previous ones, you can. How are we doing? Okay. We're kind of amping it up. We only did square roots yesterday, but now we're mixing up the type of function we're using. All right, let's try the next one. What is in the equation for f of x that's going to hint us as to what graph we should start with? The 3, which one? Get the cubed root. Okay, so the little 3. So that little 3 is not a transformation. It's not a change. It's just a hint. So let's graph the parent cubed root picture. It's actually at the top of your page if you need to reference it. All right, so the little 3 just tells us what to start with. Everything else, though, is a change, so we need to identify those. What do we see? Good, Shane? Not Shane. Seth. I'm sorry. Seth.
The negative looks like a Y.
Y, good. Y-axis flip. Good, Emma?
The 2 under the cube root will move it to the left 2.
You would think.
Oh, because it flips to the right.
Mm-hmm. This one's to the right, because the negative in front of the x is there. Last one? Yeah? Down 3, good. All right, I think we're good. RST, we identified a reflection. So this time it's over the y-axis. We got to move things left and right. So let's start with maybe this first left point over here. If we're going to take this point and fold it over the y-axis, it's going to land somewhere on the right-hand side. The next point at -1, if we fold it over, will land at +1. The origin is going to stay right where it is. The next point, though, is at positive 1, and if we move it over to the left, it's now at negative. And the last point at positive 8 on the x-axis would move over to negative 8. So we kind of have double flipping to do here. You have points on the left that you have to fold to the right, and then you have points on the right that you got to fold to the left. Okay, you got to flip everything. So we'll label that one R. No stretches, one less thing we got to do, but we have translations. So let's move the reflected graph left 2 and then down 3. I'm sorry, right 2 and down 3. Thank you. We'll label it T and circle it for the final. Or erase the previous ones, whatever you want to do. You ready to try one on your own? I'm going to take the silence as a yes. All right, check out P. Give it a shot. P of X. All right, looks like most of us are good to go. Some of us are still working, which is fine. Okay, keep working, but we're going to check it out. What was in the equation that hinted you to the parent function? What do you think, Emma? There we go, power of 3. So cubic. So we'll graph the beginning one. 0, 0, 1, 1, and if we cube 2, we get 8. And we have the negative side as well. All right, so there's our parent. What are some of the transformations in the equation? The little 3 was the hint. Everything else is a change. What do you see, Keith? Say it again. Y-axis. All right. Yeah? Right 4. Good. Yeah? Up 1. All right. RST. So reflection, y-axis flip. Everything on the left will move to the right. Everything on the right moves to the left. Bless you. There's our reflection. No stretch, nothing to worry about. Move on to the translations. Everything right 4, up 1. Label it T, circle it. How'd you do? Perfect? Awesome. All right. We're going to stop there for today. Your homework for this section, I forget what page it's on. It's a few pages in. We've done enough so far in this section that you should be able to do the front page. Okay, just the front. Now remember, homework's not due until the end of the unit, but that doesn't mean you're not working on it, okay, as we go through.